A very good morning, everyone, and a very warm welcome to this webinar. And thanks for making some time to attend this webinar on the 3D experience SIMULIA and ABAQUS SOLIDWORKS. So let us start with this webinar: optimizing design performance with nonlinear finite element analysis and multiphysics simulation. So let me introduce myself. My name is Anirudh Dayachat. I work at Beacon, that's Best Engineering Consultancy Private Limited, and I take care of technical operations for Mumbai branch. And along with me, I have my colleague, Mr. Piyush Dhuri, who works as an application engineer and handles CAE products, and also from Mumbai branch. So what I request you here is we are available on LinkedIn. I believe most of you have access to LinkedIn on your personal accounts, on your corporate accounts. If you can share your feedback of this webinar on the LinkedIn, that would be really helpful for us to improvise on our next upcoming webinars. So here is my LinkedIn profile. You can use these hashtags while posting some comments or some posts on the LinkedIn, and you can tag Best Engineers Consultancies. So having said that, let us quickly look at people who are new to GoToWebinars. This is how we can use GoToWebinars. There is a the full screen mode here, which you can always use. And one single click will take you to the full screen, and another will take you back to the restoration. And then we have a questions panel here. At any given point of time, if you have any questions, you can post it. But we do have a dedicated Q&A session at the end of this webinar. So I kindly request you all to note down your questions, and we can take them one by one and answer it in the Q&A session. And also we do have a raise hand button here on the viewers panel. If you at any given point of time, if you're facing any difficulties, please do use this button, and we'll try to fix it as fast as we can. So let us quickly look at the agenda for today of this webinar. So we'll start by introducing a particular tool called as SIMULIA Structural Professional Engineer, which is again powered on the 3D Experience platform. And we are going to look at different models and different capabilities of how the ABAQUS solver can be used extensively on the different nonlinear material models. So we're going to have a quick look at plasticity models, hyperelastic models, creep model, damage models, and then we are going to throw the session open for Q&A. Okay, so SolidWorks has always been there. It's a 25-year-old mature product, and we had a particular tool inside SolidWorks which used to work as an add-in called a SolidWorks Simulation. It's used to cater finite element analysis on an inbuilt CAD or a CAD amended platform on the regimes of linear, nonlinear, dynamic, and a few capabilities of explicit was made available. And also we had some thermal solvers, simplifications, all that. So now with SIMULIA Structural Professional Engineer, what is it that we are offering? So this SolidWorks simulation had fair capabilities of solving simple physics to mildly complex physics. And on the expanding the portfolio, we have the SIMULIA brand, which again has various tools in terms of how the finite element analysis can be leveraged. Now with this 3D experience platform, we have a greater flexibility in terms of how this particular domain of SIMULIA and a very large ABAQUS solver capabilities can be accessed to every user who has either been using SolidWorks simulation or using any other kind of FEM or any 3D CAD analysis tool. So this particular tool is called a Structural Professional Engineer, which is going to cater some of the complex physics problems. Okay, and having said that, again, this is powered by cloud-based 3D Experience platform. Now, what is 3D Experience platform? We are going to have a brief look at it, and we do have some upcoming webinars which will explain you in depth of 3D Experience platform. And now this particular, let us not dilute the agenda for this today, so I'm not going to talk much on the 3D Experience platform in this moment. Okay, so let us look at now what are the evolving needs when it comes to CAE, or very specifically on this webinar, we are talking about finite element analysis. So physics capabilities. So as the products are evolving, as the complexities are evolving, as the customer demands are increasing, there is a need to solve more and more complex physics and large scale problems. And having the need to solve complex physics and larger scale problem always needs a computer resource. So of course we need a faster and remote computing capabilities where a user will be able to access the simulation, the solver, and the workstation remotely from anywhere, would be able to review the results, give his feedback, ask the team to rerun the analysis, make the geometric changes, and most importantly, ease of use, ease to share. Right. So these are some evolving needs which we have jotted down. And how are we catering it? We are catering it using 3D experience values. So on the 3D experience, we have SIMULIA technology, and ABAQUS solver on nonlinear and multiphysics is being offered here. And we are offering high performance computing on cloud or cloud computing. So, at any given point of time, we'll have flexibility to run complex physics problems on the cloud. And best of all, this this particular technology will be made available on the subscription model. Now, what is subscription model? Is pay as you use kind of a scenario. So let us not get into more depth on the commercials part of it. But this good thing to know here is it's offered to you as a subscription-based model. And we have integrated workflows depending upon independent of CAD, or it can be dependent or independent of any kind of a 3D CAD applications you're using. And most of all, the collaboration has been made very easy using web apps. That means we have a very powerful, lightweight visualization tools where the complete simulation review can happen on the thin client devices, handheld devices, tablets, mobile phones. Work from anywhere scenario can be enabled. Okay. Now let us look at the demography and the democratization of how simulation has been moving and what SolidWorks Corporation and Dassault System have done to it. So any kind of CAE technology are always specialist centric, have been known to hard to use, have been complex to use, and they have been deemed expensive, and having limited computational power at the end, having hardware or HPC on the premises, and having long iteration cycles. Now, what is simulation today? So this democratization is happening to make simulation very powerful and easy to use. It has to be integrated with 3D CAD authoring platforms. It should enable quick design changes. It has to be fast. It has to be cost effective. It should give you a good result visualization. It should make use of cloud computing technology, and it has to be a part of a complete product design process. So have we reached the democratization today? Not yet, but we are on the way. So this is where we are trying to reach. Okay, so there is a first survey coming up. So feel free to make use of questions panel or the survey panel, which is going to pop up in front of you. So I would like all of you, I guess the poll is now open. Okay, so the first survey which I would like to personally understand from all the attendees, I guess we have more than 66 plus attendees. In your organization, do you use any kind of a physical prototype for evaluating product performance? So I guess there are 3 options made available to you. I kindly request everyone to go to the poll section and start polling. Yes, I can only see 38% of people have voted. So we can I quickly see 100%? Okay, we have reached 55. That's a quick response. Can we see 70% at least? Okay, thanks a lot for your quick responses. So we have around 22% of users telling that yes, they do physical prototypes for all of their products. And we have 45% of people uh, who voted for yes, they do prototypes, but only for main products or commercially viable, commercially important products. And also there are 38% of people who say we don't need physical prototypes, we don't use physical prototypes. Okay, so thanks for your response. So let us move ahead. I guess there's another survey coming your way. Okay, so I guess the poll will pop up on your screen in a few moments. Then the second survey is about, in your organization, are you using any kind of CAE tools, or either it could be FEM, CFD, or any kind of a CAE tool? So can we have the poll? So the 55% of people have voted. Slowly reaching towards 60. Can I see some more votes? Wow, the results are really amazing. I can see more than 70% of people are already using CAE applications in the product design cycle. And there are 33% of people who say they do not use any kind of assimilation software in the product design cycle. So that's a really great number. I was astonished looking at 70%. Thanks for your responses. Okay, so having said that, so let us quickly give a glance on what is this webinar today. And to do that, I would like to call upon my colleague, Mr. Piyush Dhuri, who will take you through a few of the slides in this webinar and explaining what is this webinar all about. Okay, Piyush, it's all yours.
Yeah, thank you, sir. We'll first see some quick glance about what is a nonlinear system. So nonlinear system is a behavior of a structure due to a current displacement, or we can see a relation between the strain relation between the particular material, or it's the dependency on the force. So you can see on the graph on the right side the difference between what is the linear behavior and what is the nonlinear behavior of a particular product. As you can see in the nonlinear behavior, as we increase the force, the structure tends to have a large number of displacement, or sometimes it also go for a hardening purpose. So we can say that the nonlinear system is a force displacement relationship becomes a nonlinear. So there are actually three types of nonlinearity, as you see in the particular PPT. First one is the geometrical nonlinearity. Second is due to the material or the material behavior, and the third one is due to the contact or the self contact. Each nonlinearity can exist separately, or they can have a conjunction, or at a time it may be a case where all the three can come into the picture. So according to nonlinearity, we have some nonlinear material models, or we can say the types of material model which assumes the nonlinearity, starting with the plasticity, where you can say the material, the metallic material, or it can be a plastic or some other granular material go under a stress strain beyond the LD, where we can use the plasticity model. Then we have something called as hyperelasticity, generally used in the rubbers and the gasket material, where the material is not compressible or it is an incompressible, but it has some hyperelastic, or it goes a large amount of displacement in the analysis or in the behavior. Then we have something creep or viscoelasticity, where the material go a particular strain rate after a significant time due to the elevated temperature. Also, we have something called as anisotropic or orthotropic, where the material behavior change with respect to the direction. So some of the examples, you can see the wood, the thermoplastics, and the fiber and composites. Before moving forward, we'll also see an example, what is the difference between actual linear material and the non-linear material. As you see on the screen, a simple example of a linear spring which obeys the Hooke's law. The spring stiffness is constant. It does not change with respect to the application of the force. And from that, we can easily conclude in a single step what amount of force is required to get a particular displacement. Or we can do also reverse, where we can check what amount of displacement is happening due to a given force. So this is a single step. The equation, what you see on the bottom, is what it applies. That is F, or that is force, equal to K into X, where X is the displacement and K is the stiffness of the particular product. So in our case, it is the stiffness of a spring. On another hand, if we see for a nonlinear material, we can see the K is a function of X, where it is totally dependent on the displacement or on the force what is applying. And on the graph also, you can see how the graph is actually varying with respect to the displacement. So initially, it obeys a little bit linear behavior, but as we move on by increasing the force, the stiffness of the material changes with respect to the displacement, and we can see the equation has been now changed. So for such method, we cannot do a single step analysis. For such case, we have to perform an incremental method, where the force is increased by a small steps, and at the end we get the final result from that. So one of the method, we use it as a Newton-Raphson method. Yeah, in this slide we can clearly see the material behavior. This is a typical stress strain curve for a low carbon steel, and you can see on the right the machine where we perform a uniaxial tensile test to get this particular graph. We can see from that the initial behavior, how the material is initially obeying the Hooke's law till its elastic limit, and as it reaches the yield point, we can see the graph or the strain is increasing drastically, even with a minor amount of increase in the stress. And at the end, when it reaches to its break point, we can see the breaking. So all this particular phenomena can be easily analyzed inside our software SIMULIA. So there is a phenomena called as strain hardening, where, let's say in this example, if you see, once the model is loaded, its yield strength, it reaches to its yield strength, and let's say if we keep on increasing the load on it to above its yield limit, you can see the data. You can see the data how it is reaching the yield strength. But as we go beyond the yield strength, or we stop at the above a yield strength, we can see, and let's say if we unload the data, let's say if we unload the load which is acting, we can see it does not reach to its original position. There is a permanent strain or permanent deformation happening in the product. But let's say after the permanent deformation has happened and we again reload it to the previous loading path, we can observe the yield strain what is generating inside the material is increased. This phenomena is called as the strain hardening or the harden. So that particular data can be also put inside our software to understand the behavior of a particular product. So here are some example of how to perform some example of a nonlinear analysis or a plastic analysis. One of the example is for a metal forming. You can see how the metal plate is being formed, or you can also see the bending of a particular bar. We can also do a multi-step analysis, as you see on the bottom right, where you can see the forming process in a single step and then multiple other steps. Not only that, we can also perform non-linearity on a material level, like in case, let's say the material is rubber or a plastic, where the deformation will be very high, as you see in the particular slides. Another thing which you can take into consideration is the self-contact. In the case of, if you see in some of the examples which are demonstrated here, Cell contact also came into picture for a nonlinear analysis. So such nonlinear analysis can very easily perform inside our software. Not only that, let's say if the load is overused or it is misused, so such type of high-end nonlinear analysis can also be very easily performed. Like in the example, you can see the crushing of a can or the particular bar, and how the nonlinear or the self-contact is getting generated. Yeah, we can also perform a 3-point test on the particular product, as you see on the left side of the slide. We can also do a failure analysis, like you can see the failure of a particular product, or on the top right you can see the tensile loading and universal tensile loading and how the product is getting break or fracture. So here is the first case study what we are going to demonstrate here, the bending process of a particular bar, as you see in the practical phenomena as well as how we can do it inside our software. So what we are going to do here, the good thing about this software is that, good thing about the SIMULIA is that we don't have to hardcore work on the particular context. We have a single tool called a general context, where it takes into consideration all type of context what we require for the analysis. We have the flexibility of using a different type of elements, like we have a tetrahedral and hex or a brick element, which can be very easily used for a particular geometry. High precision results are acquired at the default dimension or the default element. So you don't have to do a multiple iteration for generating a different mesh and understand where the mesh refinement should be done. Not only that, like you can see in the particular example that this is a 2-step analysis, loading and unloading. So both the steps can be done in a single window. So such type of multi-step analysis where the loads are varying can be easily performed here. And the time required to run this analysis is very quick. So here we can see how we can import a particular geometry which is made inside a SOLIDWORKS. Once the model is loaded, we can go and start with the structure model performance, and we can first start by creating a FEM. So here using the swift mesh, you can see how we can easily create a brick element inside a particular simple geometry. And wherever the geometry is little bit complex or have some fillets and all, so there we can use a tetrahedron or a tet element. Once this is done, we can define some context, like here I want to make this particular 2 component to be attached or be together in the analysis. So that can be done using a tie rod. Apart from that, we can also specify the material and the sections, like here you can see in the window. We can specify the material and the cross section of it. At last, we can specify some boundary condition that in our case, this is going to be hinged at the center, and we are going to specify that it is going to rotate by 180 degrees Celsius, 180 degrees. So that can be specified in the single window. So once we are defined the boundary condition, then we can perform the multi-step analysis. We'll do a 2-step analysis starting with the loading. So in this case, we will load the data. We will define the time step and what will be the initial time step and what will be the maximum increment software will take into consideration. So second step, we'll perform the same. We'll create a second step, unloading process. We'll define the time step for that. Last, we will define a general context where we can define how the context is being generated. Like once it is getting loaded and unloaded, so how the 2 components are going to interact. So that can be performed, and how the sliding effect should be taken into consideration. So here you can see the tangential and the normal behavior. We can also specify the coefficient of friction between them, and then we can apply that particular contact property in the general context. So once this is done, we can solve it on a local, or we also have a cloud computing technology where you can quickly solve on a cloud basis. So here is the general result of the displacement, and you can see how good animation software has created for us, and you can see the displacement of both the steps, that is loading as well as unloading. So this is the plastic strain which is getting generated as expected. It is getting generated at the outer and the inner area, outer and the inner diameter of the particular bar. And this is the active yielding process which is happening as the loading process is going on. Not only that, we can also check the contact pressure. As you see, the contact pressure is actually getting generated as the bar is getting bended. Next example, what we're going to see is for a hyperelastic material. So hyperelastic material are the material which show a significantly or a large strain for a given stress than the metals. Okay, so generally the rubbers, the neoprene, the natural rubber, the silicon rubber, the nitrile rubber, the chlorine rubbers are the hyperelastic material. So for hyperelastic material, we have a multiple models which we can we have to run the analysis. So one of the model which we are going to discuss here is the Moonie model. It is based on a strain density, generally used for incompressible material, incompressible rubber, and mostly agreed for a strain up to 150. We are going to use the n equal to 1, and from that you can see the equation where we require some constants like C10, C01, D1. So these are the constant what you can get from the physical data, and once you have the data, you can input that particular data in the material database. As you see on the slide, we have a various types of material model available here. What we are going to use in our case is the Moonie. So here you can see the same constant which we saw in the equation base are being inputted here. And once the data is fed, we can do hyperelastic analysis on a particular rubber geometry. Another example for another modeling, that is for a polynomial, where you can see the various types of constants and for the power of 2. So here the data curve fitting can also be done inside our software. So we have an inbuilt tool where we can do a curve fitting tool. Apart from that, you can also get various website based tools like you can see on the particular slides, where you can do the curve fitting for curve fitting analysis also. Yeah, what we have in SIMULIA is called as a material calibration tool. So in the future webinar, we will also discuss how we can do a material calibration inside the SIMULIA tool. Another model we have is a Ogden model. It is again on a strain based density. Generally, it is recommended for a higher strain where the strain is above 500 or 600%, and it is more robust or more easily solvable than a Moonie type of model analysis. So here I have an example of a rubber, and you can see how it is getting deformed, or you can also check the self context which is getting generated in the analysis. So again, this comes under a nonlinear domain where the multiple self-generating contact is being generated, and it is very quickly or easily being solved inside our software. A little slow move to understand how the self-contact or the stresses are getting generated. Not only that, you can also observe at the bottom how the contacts are getting generated, where let's say you can observe the sliding of a particular rubber on that particular plate is also happening. So that all things are very easily taken into consideration in using the general contact tool. Next example we are going to see for a hyperfoam. So hyperfoam is a type of a rubber-like material, but it has a very high compression behavior. So it is not a hyperelastic, it is a hyperfoam material. Some of the examples are foam rubber, polyurethane, latex, and etc. Where we can generally in this case the deformation is very large, even the displacement is very large, and the application we can understand the comfort or the contact pressure what the foam material is generating on a particular human body. Some of the examples like cushion mattresses, chairs, and sofa where the application of hyperfoam is generated. So this is a quick understanding of the material modeling of a particular hyperfoam material, and you can see the various constants and the potential orders and the Poisson's ratio of that particular material what we have used for our example. So here we have already created the hyperfoam material. We just apply that particular material to our particular hyperform geometry. Apart from that, we have applied a general contact, and once the analysis have run, one more thing in the observation, you can see we have not taken the whole geometry, we have taken the 1/4 or the quarter geometry for the analysis, and you can understand how it is getting deformed. We'll see this particular example live later. Yeah, one more thing you can observe here, how the general contacts are working. So instead of bonding the particular hyperform to the base, it is getting lifted up at the other ends. Another tool what we are going to see is a creep model. So creep is a permanent deformation of a component under a static load maintained for a period of time. Mostly it is observed in a metal, which metals and their alloys generally not on the room temperature, at a little bit we can say at an elevated temperature we get the creep strain being generated. What we are important here, we are going to see how we can estimate the life of a product using the creep model or the creep analysis inside our software. So in this application, we have taken the consideration of a pipe with a side tube, and you can see the dimension of that on the top right. And what we are going to do, we are going to apply an elevated temperature of around 540 degrees Celsius and the internal pressure of 14 megapascal acting on that particular pipe. So here are the steps what we are going to do in this particular analysis. We will create a static and a quasi-static analysis. We'll define some restraints, how it is being fixed, or the symmetrical model. So we'll specify symmetry constraint. Then we'll apply the boundary condition, that is the temperature and the internal pressure. And once this is done, we can run and estimate the life of it. So here, the additional step we have to perform here, we have to tell the software for how many years or for how many days we have to check the particular product's life, or after how many years, how many percentage of strain is getting generated, or we are getting exposure. So here we have specified 50 years. Apart from that, we have specified the time increment here. And then we can also take into consideration the geometrical nonlinearity, which is happening due to a prolonged exposure to a temperature and the pressure. So here we can see a live example of the particular tool, and we have specified everything from the creep law. So here you can see the various types of creep law or the material models we have, starting from strain hardening, time hardening, power law, and every others. Once this is done, we can quickly check the amount of strain is getting generated in the model and where it is getting strained. So this way you can quickly do a creep analysis on your particular product and understand its life. So further to this particular presentation, I will hand it over back to my manager, Mr. Anirudh. So he will continue with the further presentation.
Thanks, Piyush. Thanks for the insight on the different nonlinear material models. So moving ahead from the nonlinearity, there are different kind of damage models also present, and that can be modeled very accurately in our SIMULIA softwares. So let us have a quick look on what are the different damage models that we have, what is the damage response, how the damage propagates, right? So all this starts by something called as progressive damage and failure. So components of material definition. So basically what we do here, we define something called as constitute behavior. So there is nothing but we need to define how the damage initiates, how the damage evolves. So this is a very important parameter that defines how the damage progresses. And at this point B is something where we reach choice of element removal. So we'll see this live, how this works in some time. Okay, there are different kind of damage that may happen. Now here in this particular webinar, we are discussing on the ductile damage. Damage initiation criteria for ductile basically, and similarly there can also be brittle cracking, which will come up in our upcoming webinar series. Right. So here we all know that the uniaxial stress strain curves. So when it comes to damage models, there is something that comes into picture is triaxiality. Or it's also it's also denoted mathematically like this. So we are going to use this criteria or the ductile damage criteria to define this behavior, right? So how that can be behaved again, how that can be modeled here is basically the complete behavior is controlled by material modeling. So we are going to use this ductile damage. We are going to have this data, on what is the fracture strain, what is the fractality indicator says, and what is the strain rate. Okay, so this is how we are going to define it. Okay, so there are a few different kind of damage evolution that may happen. Okay, so one is the post-damage initiation of the material behavior that can also be found out. Okay, so now this formulation is completely based on the scalar damage approach. Okay, so this is how it works. Now we will also look at in another part of damage evolution where elastic plastic materials. Okay, so this is called as degradation of elasticity. So even this can also be taken into account while making a material model. So now what has to be considered here? There are two major points, or the softening of the yield stress. Okay, so this is the curve which defines the softening of the yield stress. And then there is degradation of the elasticity. So this particular curve, what you are saying, mathematically 1 minus d into E. So that is going to define the degradation of elasticity. So this material model can also be done on the SIMULIA software. Okay, so there are multiple other damage evolution methods. Either it could be in terms of fracture energy, that is per unit area, what is the energy of fracture that may occur. So that can be also be formulated. Okay, so what we are going to do, we are going to see this example live on how we can do this material modeling. Now, let me take you to the screen of my 3D experience platform, and let me just get a confirmation from my colleagues where my model is visible. Right. So this is the user interface of how the 3D experience platform looks like. Now, this is a unified platform. Now, what do I mean by it when I say unified? So here, the complete applications on the 3D Experience business platform has been offered to you as different apps, and each and every different app work depending upon the evolution and the need. Now, if you can look at the same platform, I do have a few of the applications powered by SIMULIA, and similarly, I do have some of the applications which are powered by SolidWorks, and few of them are from the CATIA. So this is a unified platform. Depending upon what my need arises, I can quickly switch back to the either the 3D modeling, or either I can switch back to my mesh modeling, or I can switch back to my complete finite element analysis or solver post-processor or pre-processing models. So as you can see in this model tree, we have a small 3D shape. What we have done, we have taken a symmetry and then I have mirrored it. Okay, on this I have created a finite element model. So in this finite element model, I have used a brick element. So I have used a meshing technique called as a 3D sweep mesh, and I have defined a section property of it, saying it to be a solid section, and then comes the material modeling, which is the most important parameter here while modeling the damage. So here, let us take a quick look at the material modeling. Okay, so here I have defined the behavior of how this material is going to behave. So inside ABAQUS multiphysics, so I need a density as a function. I need elasticity as a function, which is defined by Young's modulus and the Poisson's ratio. I have defined it to be an isotropic because it's a steel. And I also want it to be have a plastic behavior. So inside plastic behavior, I can have multiple plasticity model. So for this specifically, I'm going to focus on metal plasticity. In metal plasticity, I have defined the plastic behavior on the yield gradation. So yield gradation, I have considered it to be von Mises. And isometric hardening is to be considered here. We can also do kinematic hardening problems or a combined hardening problems depending upon the need. And we can also define different isotropic hardening models. So here I'm using a tabular model, and we can also use Johnson-Cook isotropic hardening model as well. Similarly, we can also take into account strain rate dependent data. So we can define that. We can use temperature dependent data. Okay, but for this, I'm just defining yield stress versus plastic strain. Okay, so this is the plastic behavior. So once this is done, as we are talking about damage, we also need to model damage. So inside damage, again, we have different damage models, as you are able to see here. Okay, we have one of the model called as a ductile damage model. So inside ductile damage model, I need to define two parameters. One is how the fracture strain versus stress triaxiality indicator is going to behave versus my strain rate. So as you can see, the strain rate is uniform, but my stress triaxiality is varying with the fracture strain. So this is what we have defined here. And then what I also need to define is how the damage evolves. So we had seen that on the curve where from the point A and the point B, how the softening is happening. So here we have a linear softening that has been defined. Similarly, here the evolution of the damage is being defined using a displacement method. The same thing can also be done on the energy-based methods. So where the fracture energy can be captured and given as an input. Okay, and then displacement of the failure can be defined, and degradation can also be specified. Okay, now once this is done, let me move back to my physics results. Right. Now once this is done, if I'm done with defining my material, the next thing here is I've defined a scenario. So here in this non-linear static analysis, so I have defined the solver setting. So basically I want the complete analysis to step time is 1 second, increments are around 1000. Okay, and the initial time increment is 1 second. So, and there are few stabilization, energy fraction stabilization has been defined. And I have asked it to include geometric nonlinearity if it may arise. Okay. And once this is done, as Piyush had showcased to us on how the solving can happen. So the SIMULIA, structural professional engineer on the SIMULIA does offer cloud compute. Okay, so the cloud compute is going to let me use different cloud computing techniques. So we're going to look at it in our upcoming slides and examples. So let me quickly load the results. Right. So now here on this front, on the one particular static step, there is a nonlinear static step what I have defined. So these are different plots. So let us start by adding a von Mises plot. So here, as you can see, the von Mises plot. Here we have a sequential results, and quickly here the probing can also be done just by moving the cursor over a particular area, and also the results can be extracted at the elemental level, Gaussian point level, or either it could be at the nodal level. Let us quickly have a look at the animation. I guess it's a bit slow depending upon the frame rate. I hope you'll be able to visualize it. You can see the stress evolution and also the yield softening phenomenon at this particular juncture where the necking is happening. So this damage evolution can be modeled depending upon the applications. And another great way why the SIMULIA on the 3D experience works has a greatest integrated technology, and why we call it as a business platform is because we can have a complete review-based model along connected with the PLM. So as you can see, each and every simulation models are connected with the PLM technology, where the complete workflows can be maintained, the complete PLM history, the revision management, collaboration, as well as lightweight visualization. So we are going to come on, I'm going to come back to this on how the lightweight visualization can bring in a lot of collaboration between the teams, within the single window integration. And as you can see, I'm using a web browser to access all of my physics results. So again, those physics results are, as I told, it is a lightweight visualization. So here I have multiple results plotted. So as you can see, I have mode shapes, I have one meso stress, right? And these are not static results. It does have the complete the information, the results saved at the regular time intervals. You can evaluate the complete legend, and all this is happening on the web browser. And same thing holds good even on the the handheld devices as a thin client devices as well. And the same way, the complete simulation can be animated here. Let me quickly load back a mode shape so that it will give me an exaggerated view. So this lightweight visualization is going to give me a greatest way where I can collaborate with my team members and different stakeholders and communicate my ideas using something called as a community. Now, a community is a great way where we can collaborate with a complete team set, team members, the complete organization on the platform and make collaborative decisions together. So as I told, I'm not going to dilute the focus much on the other functionality of the platform in this webinar, but we can have a look at it in a few of our upcoming webinar series. So moving back to my presentation. Similarly, different kind of fractures or different kind of material failures or damage models can be prepared, and different X5 plots can also be uh, taken from the field results. Okay, so now let us quickly have a look at one of the tests called as an you must have seen it during our so we must have seen this particular impact test in terms of a materials lab, understanding what is the impact strength of a particular specimen, right? So we have a very close, as you can say, a very close correlation between the actual test and the analysis done on our SIMULIA's product suite. So we'll just have a quick look at this video where a person is calibrating that Charpy test bench for the exact position of the swing or the hammer. Okay, now what this does, so the same thing has been replicated on our SIMULIA software, Tactile Professional Engineer. As you can see in upcoming slides, the evolution of damage is more closely captured here in a few of our more images to come. And as you can see, the correlation between the actual damage and the one that has been provided by our software. We have a very close correlation with this. So using this tool, and the cloud computing, we can get as close to the real lifelike simulation problems. And yet another example on the damage model here is on the tube crush. As you can see, the evolution on both the screens, on the hydraulic press as well as the same thing replicated on our software, can see the exact correlation in terms of self-contact and the accurate deformations. Again, this is all possible due to the robust material modeling system what we have, and the general contact, which is one of my favorite tools inside this particular tool, which saves a lot of time in terms of pre-processing, rerunning, and understanding the results. Just by using one particular one contact set, the ABAQUS solver, the robust solver is going to calculate the contacts at different junctures during the solve process as well. So this is one of the my favorites in terms of using the SIMULIA Professional Engineers tool. So what is it that we bring to the table today with this particular tool is, it's a powerful tool. Again, it's robust and a reliable FEA technology. Again, it's powered by ABAQUS solvers. We can do advanced contact analysis, advanced meshing, and material models. Again, we have an integrated workflows. If you are a SolidWorks simulation user, all the pre-processed data from SolidWorks simulation, along with the materials, features, and the model, including the mesh, can be pushed to the ABAQUS interface. And we also offer cloud-based, post-processing as well. And solving is one part, and the complete post-processing can be pushed to the cloud-based execution. Again, saving a lot on resource requirement. And we also saw how we can share the simulation models and results using the lightweight visualization. So what are the problem statements that can be addressed using this particular structural professional engineer tool? Linear and nonlinear static and dynamic analysis. We can do frequency and buckling and the modal analysis. We can do model dynamic response analysis. Thermal and thermal stress domains can be addressed here. Okay, so these are few problem statements where we are talking about gasket sealing, rubber bushings, metal plasticity with contacts, bolted assemblies and preloads, or either it could be some kind of a coupled analysis here. As you're able to see on the screen, in this domain, we have a fluid modeled as a rigid fluid model, and the fluid is interacting within the geometry. The external contact is pressure is applied from the outside, and you can see this diaphragm being deflected due to the fluid present inside. So this kind of co-simulation and multiphysics problems can also be considered. So there is a very simple workflow for the SolidWorks simulation users. The solver is being, or the study is being defined on the SolidWorks desktop interface. Okay, if you find any convergence issue or any kind of advanced meshing modeling requirement, the same thing can be transferred using the connector with one click. With one click, the complete analysis moves to the SIMULIA interface, and then we can make the analysis happen using this particular tool. So this is one integrated workflow what we have for the SolidWorks simulation users. Okay. And above all, it has been powered by SIMULIA. We've been talking a lot on SIMULIA today. So it's a world technology leading. It's a world leading technology and the finite element analysis software. So these are the multiple domains that can be addressed. As I told, close to life or the real life kind of physics problems, multiphysics problems. We can have a co-simulation in terms of different interactions. Either it could be a fluid structural interaction, that is a one-way, or a two-way fluid structural interaction. Either it could be a co-simulation between thermal analysis, or a co-simulation between electromagnetics. So all of this can be addressed using our connected solutions. And similarly, we have a very robust explicit solver on the ABAQUS explicit in terms of modeling, different complex physics. The one you are able to see on the screen again is being done with the help of the general contact. So what does it include? It can handle multiple nonlinearity effects. So I guess Piyush was talking on one of his slides on the different nonlinearity and how they can coexist in one environment. So it can handle nonlinearity with ease, have very short run cycles, and it comes up with some of the complex material library, in terms of the material models, which comes inbuilt as a material library. And it has different industrial workflows, very set industrial workflows for running multiple analysis. Again, adopted from the industry experts. And coming to the meshing techniques, we do support different advanced meshing techniques. We must, in some of the examples, you must have seen the hybrid mesh, what we must have used using the tetrahedral elements, brick elements, and the continuum shell elements. Similarly, as you can see, we can do multiple other meshing. So we can have a rule-based meshing, we can do continuum shell mesh, we can have a quad and brick elements, or a complete mixed meshing techniques. So coming back to my favorite topic, that's the robust general contact. So this is the one. I know. 70% of the users on this webinar today. I believe you will trust me on this and also vote for me because defining the contacts and one or couple of contacts going wrong can uh, you know uh, take the credibility of the simulation, whatever has been spent in terms of either time, manpower, and the computation expenses. So this particular robust general contact is going to be a savior in terms of multi-contact or self-contact problems. So how do we say it? It's one feature function for all kind of contact problems. So self-contact, sliding contact, multiple complex contact and friction modeling. So for all the needs, there is only one solution. That's one option and one feature called a general contact. And as I talked about the cloud-based computation, so you can always leverage on the cloud-based computation depending upon the the license credits. So license credit computes depending upon how many available of runtime is available. What will be the number of tokens or credits that they're going to get consumed while using the cloud-based HPC, or you can always choose to run the analysis on your local machine. So the freedom lies with you whether to go on cloud or onto you can run the simulation on your local workstations. So we also had a brief touch base on the collaboration, how the collaboration can happen. We can share the lightweight results via web browser. So web browser can be on your any device, any handheld device or thin client devices. And all of this data is mapped through a PLM. So that is again powered by NOVIA technology, again the world trusted technology on the PLM front, and are safely stored on the collaboration spaces. So we're talking a lot on cloud, so definitely we'll have to talk about the security on the cloud and the downtimes, which are the factors to be considered. So as this particular platform on the 3D Experience platform have been offered on 3 different models. We have software as a service, platform as a service, and infrastructure, which is also offered as a service on terms of cloud computing, data storage, data hosting, and the PLM. So all of this have been certified by relevant ISO standards. And when it comes to the platform, it is also certified by one of the highest aerospace and defense standard, ISO 17799. Okay, so these are the certifications on the Dassault System cloud infrastructure. Okay, so these are few of our upcoming webinars. We are going to run a webinar series on explicit dynamics, and we have a few webinars coming up on fluid dynamics and fluid. The fluid SIMULIA fluids is a very wide and very large domain. So we are going to have some series coming up on it addressing different industry challenges. And then we have webinar series coming on electromagnetic analysis on again SIMULIA CST product suite. So again, we are going to leverage different electromagnetic analysis there, EMCs, EMIs, microwave, RF, antenna placement, antenna design. And then we also have another webinar series coming on plastic injection molding. So which specifically addresses the challenges in the tooling and plastic part design domain. Okay, so this is a quick view of what you can expect on a few upcoming webinar series. Okay, that takes us to the survey number 3. So I would like to, or we as a Beacon would like to take your feedback on what was the interest. Were we able to create some interest by running this webinar. So I guess the poll should be up and live in a minute. Can we see the poll? Okay, already 14% people have voted. Okay, I can see around 60% of people have voted, which has been our benchmark on the today's participants' interest. So can I have some more votes? Can I request all the participants to participate in this polling? Let us break a benchmark of above 60%. I can see 64%. That's. Thank you for that. Shall we stop collecting the votes? Okay. Thank you all for the responses and results. Should we share the results with them? It's shared already? Okay, great. So the 55% of people says it's very interesting. Okay, and we have around 45% of people saying medium, some interesting points. We tried our best to include the best content, and surely with this feedback, we'll try to make our webinars more interesting with more relevant content. And as we always say, we have that questions panel open for you. We are open for suggestions. At any given point of time, if you want to suggest us on how we can improve our webinar series or what content to be included, we'll be very happy to get that feedback, work on it, and get back to you with the the interesting content so that we can engage in a more better sense. Thank you. I guess that we have another survey coming up your way. Okay, so which I just showed you what are the next webinar series we are planning to do. So these are the 4 different webinar series that we are planning to do. We are planning to have a structural explicit analysis using SIMULIA explicit solvers, and computational fluid dynamic on SIMULIA fluids, electromagnetic simulations on SIMULIA CST suite, and plastic injection molding analysis on SIMULIA plastics. So which of the webinar series would you be interested in? And you can also you can have multiple choices here. No, okay, no, there are no multiple choices. You can vote for one. You can vote for one, and we'll try to get that webinar up and running on our next series. Oh, whopping 50% of people are voting on explicit as expected. Only 4% on electromagnetics. We can see around 25% on plastic injection molding. Closely around 18 to 17% on CFD, computational fluid dynamics, SIMULIA fluids. Okay, I can see 66% of people are participating. So can I see some more? So let me keep this poll open for next 15 seconds. Okay, so let me see if I can collect some more inputs. Okay, we have broken the barrier. We have reached 70% of voting. Thank you so much. Okay, that is it. So your suggestion is our command. So next webinar is going to be on the structural explicit analysis, followed by plastic injection molding, and then the computational fluid dynamics and the electromagnetic simulation. So that is how we are going to do it. Thanks for your responses. And we have your email IDs. We'll keep in touch with the next webinar updates and the calendars. Parallelly, you can follow us on the different social media platforms. Best Engineering Gates Consultancies Private Limited. We'll also share you the links of different social media platforms. You can keep following us there, and you'll get all the updates on the webinar series or any kind of technical know-how series that may come up. Okay, so let us open this session for Q&A. So you can ask your question here on the questions panel. You can type your questions here. We'll read it out, and then we'll try to answer that question. If you do not have answer to your question readily, we'll get back to you on email. So I hope that should be fine. Okay, so let us open the questions panel. Okay, we have the first question. What is the accuracy of simulation related to the sheet metal? Sir, the accuracy cannot be defined on the model type. If you're talking about sheet metal, we'll have to look at how it is being modeled. So basically, there are two different approaches. One is how you model it using your 3D CAD authoring platforms, and that is independent of the accuracy. Basically, if your dimensions are right, if you're falling under the, if your the tolerances range, so the geometrically it will be right. And next part is the finite element modeling. So finite element modeling, majorly your result accuracy will depend on how well you are going to capture the mesh, what kind of mesh elements are you going to use, what are the ordered element sets you're going to use. So basically, type of elements. So either it could be, as you're talking about quantum shell elements, specifically on the sheet metal related query. Yes, we can do quantum shell element modeling. Again, you can choose to have a quad or a tet elements depending upon integration levels. You can have hybrid order integration or reduced order integration elements, and then your complete accuracy depends upon that. I hope you have answered your question, sir, in the right sense, if this is what you had asked. I have another question coming up. Can you please elaborate ABAQUS module? Sir, in this session, it won't be possible. It's a very huge domain in terms of understanding ABAQUS altogether. We can definitely, have a session with you one-on-one. We'll be in touch with you, and definitely we'll be, more than happy to let you know what exactly we mean by ABAQUS module. ABAQUS is basically a solver, so it's a SIMULIA. We can call it as a SIMULIA portfolio. Okay, there is another question coming up. Hi, is there an airflow analysis and aerodynamic simulation can be done? Yes, sir. Yes, that can be done. We do have SIMULIA fluids on the different regimes. We have different technologies which can handle CFDs. Either it could be in terms of static geometry, moving geometry, or either it could be a flexible geometry, variable geometry. Yes, we can do aerodynamic analysis. We can perform aerodynamic efficiencies, your lift to drag ratios. Yes, that can be done. Can we see simulation of mixing of powder and liquid in a screw conveyor? Can we evaluate density of the mixed product? Okay. So this falls under something called as a co-simulation, which can be handled on the SIMULIA regimes. Yes, sir. The answer is yes. We can do it. In plastic, okay, I do have another. In plastic, SIMULIA shows thermoforming formulation simulation results and also solver. Sir, as of now, the plastic injection, as the name suggests, it's a plastic injection molding analysis. For thermoforming, that can also be addressed, but like blow molding, thermoforming, compression molding, that can be addressed using our different SIMULIA software, solvers. The answer is yes. We do have a solution for it. We can, we can get in touch with you to let you know more on it. Okay, I'm just going to keep the session open for some more time. Okay, is it useful for thermoforming? Sir, can you please elaborate on being useful, because I am not pretty sure how do I answer that question. Or are you trying to ask, can thermoforming analysis be done using our tool? Yes, sir. Thermoforming analysis can be done using our tools. I hope I have answered most of the questions. I'll also share the contact details of our teams, where you can personally write in your queries, and of course there will be a feedback mail that is going to come up, and we will also share the contact details where you can personally write to us and we can have one-on-one conversation. Okay, can it used in solar dryer analysis? Sir, the application, yes. When just by looking at what you say, yes, we can be. It can be done because if you're talking about the dryer analysis, then there are different ways the thermal solver can be used for moisture removal. So that can be addressed. Yes, sir. Again, it falls under the co-simulation bracket of the SIMULIA offering. I guess we can close the Q&A now. Okay. So we'll drop in our email IDs so that you can write to us if you have any further questions on this. Okay, I'm sharing contact details of my colleague, Mr. Vivek Vijayakumar Panikar, who has arranged this webinar for today and has taken a lot of efforts in bringing all of you together in one single unified platform. and making this webinar successful. And I hope it was informative for everyone who attended it, and investing your close to 1 hour 15 minutes of your time, and we are really thankful for that. And thanks, Vivek, for arranging this. And here are Vivek's contact details. You can drop an email to him at vivekp@beacon-india.com. And there is also a cell phone number where you can directly get in touch with him for any further queries. So we'll be happy to assist you on that. Okay, am I seeing another question? Okay, there's another question. What is co-simulia? Sir, there is nothing called as co-simulia. It is co-simulation. Co-simulation is basically using two different solvers. Let us say there is one. I can give you one small example of it on the thermal structural coupling. Now, let us say if you take a metal specimen and you heat it using any of the heat transfer methods. Okay, so now that particular heat transfer method has induced some stresses and some displacements. So some displacements first. So due to the displacements, then there are stresses that have been arised. So in very layman terms, I can call it as expansion and contraction. So now, if I have to analyze this, I need to have two different solvers. The first is a thermal solver to understand the thermal distribution, and then a co-simulation to be done on it using our linear perturbation methods in terms of understanding how the metal is contracting or expanding due to that particular temperature. This is one of the example. Or another example would be a car moving at a very high speeds, and as it is punching through the pockets of air, and due to its aerodynamics, I know there can be a lot of lifts and drag forces coming on the surface components or the surface fixtures of the car. Now, this analysis has to be run using multi-physics approach. So this is co-simulation, where the fluid is involved, fluid simulation is involved, then there is structural solvers are involved, thermal solvers are involved. So when we use all of this together, we call it as a co-simulation technique. Okay, so we can end this webinar now, I guess. Thank you so much, everyone, and have a bright day ahead.